now talked about chemical reactions in chapter 3 and stoichiometry. Then we talked about solution chemistry in chapter 4. Now we come to a really fascinating area of chemistry referred to as thermochemistry. Here is the chapter where we deal with energy, heat and energy, and how it relates to chemical reactions, because many chemical reactions give off energy or require energy. And so energy itself acts as either a starting material or a product in many reactions. We have to know how to be able to keep track of it and calculate it for chemical reactions. The first step, however, is to first define what we mean when we talk about energy. So, brief definition: energy is the capacity to do work or to transfer heat. And we give the symbol W for work and Q for heat. So what does that look like exactly? Well, here's two examples. So we can have chemical reactions that release heat, as shown on the left with a combustion reaction. We can also have chemical reactions that do work, as in this case, if you were to shake up a bottle of champagne enough to actually blow out the cork, then we have work being done. And I think we all have a sense for what heat is. But what exactly is work? What's a good definition of work? Well, work is simply defined as force times distance. Essentially, in order for work to be done, there must be movement of some kind. Now, let's talk about the units of energy that we will use. So there are two common units for energy. There are joules and there are calories. Now, joules are the SI unit for energy. This is more the metric unit, but it's the accepted or standard unit for energy. And 1 joule is actually defined in more familiar units as 1 kilogram times meter squared divided by second squared. That simply allows us to relate the J, which we may not be familiar with, to other units that we may be more familiar with. Now, there's also the unit of the calorie. What exactly is the calorie? The calorie has been defined as the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. So it's the energy required to raise the temperature of 1 gram of water by 1 degree. So 1 calorie can be related to joules, so that we can convert between those two. 1 calorie is equal to 4.184 joules. And additionally, you may have heard of calories and say, oh, I know what that is. We see calories on food labels all the time. So this is essentially what we're talking about, calories and calories. But we have to stop for a moment, because unfortunately, in the wisdom of the food industry, the calorie that is listed on the box is not exactly the same calorie as what we're talking about here. The calorie that's listed on a food or dietary label is actually a kilocalorie. It's often listed with a capital C, but it's essentially 1,000 of the calories that we are listing here. So 1 small c calorie is the energy required to raise the temperature of 1 gram of water by 1 degree Celsius. So 1 food calorie would be 1,000 of those calories. Now, a little bit more discussion on energy. There's 2 types. There's kinetic energy and there is potential energy. So kinetic energy is just the energy of motion. That's the energy when something is moving. We can calculate this using a simple equation you'll probably encounter in physics. The kinetic energy is equal to 1/2 times the mass times the velocity or speed squared. And then the alternative, though, is potential energy, and that's stored energy, energy that's not in motion now but could be converted into kinetic energy, as shown kind of in this example here. So if you have a cyclist who's at the top of a hill paused, they have 0 kinetic energy because they have 0 speed. So there's no kinetic energy there, but there at the top of the hill, there's a lot of stored energy present there. There's a lot of potential energy. All they have to do is roll a little bit, and then the force of gravity will pull them down the hill, and that stored energy will be converted into kinetic energy. Now, for the purposes of chemical reactions, we are just going to ignore kinetic energy, and we're only going to focus on potential energy. For this discussion going forwards, we only really talk about stored energy, the energy stored in molecules or in reactions. So a little bit more, how do we relate potential energy to atoms or molecules? Well, it might be helpful to discuss a particular type of potential energy known as electrostatic potential energy. This is simply the potential energy when we're involving two charged species. So if I've got two charges, let's just say two balloons that had a charge on them, when they're at some infinite distance from each other, they don't feel each other at all, then each of them has a particular energy that they start at, just a particular potential energy that they start at. As I bring those two charges together, however, then if those two charges are the same, if they're both positive or both negative, then as I bring them together, the energy of the system goes up because there's now force between the two. If those two are opposite charges, then there is a lot of there's more stored energy, because if I were to release those two charges, that stored energy would be converted to kinetic energy quickly, and those two charges would just bounce away from each other immediately because they repel each other. And so as I bring those two together, the energy of the system, the potential energy, goes up. Now, the alternative situation is if they were opposite charges. As I bring those two together, then if I were to release them, they're not going to repel each other, and actually they're going to want to come towards each other. And so the energy of the system goes down. And so having those two charges next to each other is at a lower energy state than having them separated from each other. So now, how in the world does this relate to compounds? Well, an ionic compound, which we've talked about a lot, an ionic compound is simply composed of two charges of opposite types, or we can have multiple ions. So we've got multiple charges present of opposite types. And if we have those ions completely separated from each other, we start at some energy. And as we bring them together to form the actual compound, to form chemical bond, an ionic bond between the different ions, then my potential energy decreases in this system. And so having the ions together in a compound is lower in energy than having them separate from each other. And this then is very fundamental and results in two observations. The first is that whenever chemical bonds are formed, whenever we make a chemical bond, whenever we bring two elements together to form a bond, energy is released or given off. If we think about that in this ionic compound example, we start out at some energy when the ions are separate, but when we bring them together, we end up at a lower energy. That energy difference, that energy has to go somewhere, and so that's just given off, since we start out with more than what we end up with. Now, the opposite case, however, is that if we ever want to break a chemical bond, whether it's an ionic bond or a covalent bond or any kind of chemical bond, anytime we want to break a bond, because we're at the lower energy when those atoms are together and we're at higher energy when they're apart, it requires energy to break them apart. That energy has to come from somewhere. And so the two fundamental observations here are, first, that energy is given off when we form chemical bonds, and second, that in order to break chemical bonds, energy is consumed or required. And that's a brief introduction to energy and its relationship to atoms and molecules. We'll talk more in the next videos and expand upon these concepts.